Go ahead and get started. Hello, everybody. Welcome to 552. Are you afraid?
Yes.
Yeah, you should be. I'm afraid too. It's my second time through teaching. I learned a whole lot last time, but I'm still haunted by the questions that were asked that I couldn't answer. So I've tried to learn some things in the meantime. We'll see how it goes. Course documents are on Learning Suite, which I think is published. If it's not, I'll do it today. I forgot to press publish, so sorry about that, but I think I sent everybody a syllabus. In any case, we won't talk about the syllabus, just read it, and there'll be some assignments to help you sort of keep up with what we're doing. And I don't know that there's anything to say other than that. So I've been here at BYU since 2011, which I realize is ancient history. Some of you were probably in junior high in 2011, and that's cool. I've been married to Amber for 20 years. I got 4 sons. The oldest is starting as a freshman at BYU today. It is weird to have him not at home, but his brother that he shared a room with for his whole life is expanded into the space, kind of like how gases expand into the space of the container that holds them. Jack has done that, and he's living his best life now. So we'll see how it goes. And then I have another, so there's Nate. Jack is a junior in high school. Let's see, Dallin is 13, so he's too cool for school, and he's in junior high. And then the littlest is Adam. Let's see if I can get, no, it's not going to show you a picture of Adam. Maybe, yeah, so Adam takes over my iPad occasionally, so you may find some strange pictures. All right. Chemistry. So we're going to begin, and we're going to use the Advanced Physical Organic Chemistry text by Anslin and Doherty. They're really great organic chemists, and the text is really good, and you can use it as a reference sort of throughout your career. We're going to start in chapter 14, which seems weird, but that's the section on sort of quantum chemistry and computational chemistry. And we'll do some math in chapter 14, but then in chapter 1, when we go back to there, we're going to learn how to do all of this without doing math at all, which is kind of fun. But I want you to have an idea of where a lot of the assumptions that we make and the principles we use in organic chemistry come from. So couple of foundational things that you're going to need to remember briefly just to follow the discussion. So starting in about the 1600s to the mid-1800s, you had the wave theory of light, where c is the speed of light, and that equals wavelength times frequency. Does that seem familiar to people? Speed of light is, of course, in meters per second. Wavelength is in meters or some length, and then frequency is in per second, cycles per second. Similarly, even if you have a wave, even if it's not a wave traveling at the speed of light, you can say the velocity of a wave is equal to its frequency times its wavelength. Okay, well, big deal. That was the wave theory of light. And then Max Planck came along, and Einstein in the early 1900s, and came up with this definition: the energy of a packet of light is equal to Planck's constant times its frequency. All right, and just for fun, the Planck constant, I guess I should capitalize the P, who cares, is in units of joules times seconds. And then, of course, frequency is in per second, so that's where you get the energy from. But the idea here was that energy in light comes in discrete packets, quanta, or photons, we call them. Some other ways that we can represent frequency, as we've said here, frequency is in dimensionless cycles per second. But you can represent frequency with another term called omega, and this is radians per second, because a lot of the math we're going to be doing involves trigonometric functions, so it's convenient to have frequency in radians per second. It turns out I learned that radians don't actually count. You know, radians versus degrees, they don't actually count as a unit, which is interesting. Didn't know that. But your frequency is equal to radians per second divided by 2 pi, because there's 2 pi radians per cycle. And if we substitute this into our description for energy, we now introduce a modified Planck's constant, which is called h bar. Okay? And people talk about this in physics a lot. This is just Planck's constant divided by 2 pi. And now your frequency for your photon is in units of radians per second, where there are 2 pi radians per wave cycle. Okay, getting sort of deep in the mud there. Einstein, with special relativity, came up with the famous equation that even people that don't know science know. This is the mass-energy equivalence. And then in 1923, a French physicist named de Broglie, I didn't know that that's how you pronounced it. I think you ask most general chem students and they're like, yeah, it's the de Broglie something or other. And actually, I guess in French, it's de Broglie. So now you know, and you can be the pretentious kid in the room that corrects the student that says de Broglie. In any case, de Broglie started with this definition of energy in packets, and then this definition of the mass energy equivalence, and sort of put it together and said, all right, well, then let's let mc squared equal Planck's constant times frequency, which, if we go up here, frequency we could say is equal to the speed of light over wavelength. So all right, let's just hc over wavelength, and that would work, say, for a photon. But let's now take the jump, and the jump is this should work. This is the part of his postulate. This should work for particles with mass that don't move at the speed of light. I feel like I'm on thin ground here, because some of you may have been about to ask me, well, aren't photons massless, so how does that work out? And I got nothing, so I'm sorry. Particles with mass that don't travel at the speed of light, instead travel at some velocity v. And in that case, he's just substituting in v for the speed of light, and presuming that this ought to work as well. And the jump is the idea that particles with a mass traveling at velocity v should have some kind of wavelength. Okay, so this gets to the principle of wave-particle duality, that there are particles of a certain mass and size and speed in chemistry that we're going to treat as some hybrid between waves and particles. And you can do a little bit of creative equation manipulation here if you pull the wavelength to the other side and then divide both sides by m over v squared. You cancel out one of the v's. And then, whoa, look at this. Momentum equals mass times velocity. So the momentum of a wave has something to do with its wavelength, which is, again, kind of interesting that a wave can have momentum, which is typically a property you associate with a particle, but then still have wave-like behavior. Okay, so all of that's a setup for us to understand where we're ultimately going here is, where did the Schrodinger equation come from? And then how can we use that to understand molecules? Okay, so if we have the idea that a particle with momentum also has a wavelength, then we need to figure out how that's going to work with how we represent our waves. So I'm going to introduce the term psi, which stands for a wave function. A wave function is simply math that describes a wave. And I'm going to represent it in an interesting way that I honestly don't totally understand. All right? You can represent a wave with the number e, 2.7 whatever it is, raised to the imaginary number. Is your head exploding yet? That's just like nuts, right? Times k times x. And this is the description for a wave. This describes the, why can't I erase that? There we go. A wave as a function of space. We're going to just leave out time to keep things a little simple. The reason we can represent a wave like that may look interesting, and you may have thought, well, a wave, isn't that something like a up and down, kind of like sine or cosine? It turns out that through some math that I don't understand, and you can actually go on YouTube for proofs of this, but if you raise the number e to the I times theta, that equals the cosine of theta plus I times the sine of theta. And that's kind of bizarre. What the imaginary number here, the imaginary unit, does is it gives the wave somewhere to go when it goes to zero. It creates the oscillation in the wave. For example, we know that the cosine, say, of, oh shoot, no, I don't know my math anymore. The cosine of pi halves is what? 0, right? Where did the rest of the wave go? Well, it went into the imaginary domain. The sine of pi halves is 1. So at theta equals pi halves, the wave function you observe is no longer real but imaginary, and so its magnitude in the real area is 0. That's kind of out there. It's a little bit strange, but you can go on YouTube and look at a proof of it if you want. But this simple representation describes a wave that oscillates like this. And typically, we're not going to worry about the imaginary part of that because we can't see it or measure it. So we'll only be concerned with the real portion. Okay, so let's see. So let's talk about what this kx part means. And we could write this out. Pull this here. Yeah, let's go ahead and write it out as cosine of kx plus I times the sine of kx. All right, let's talk about what this constant k means. K is in units of cycles in radians per unit distance. Okay, so we can define k as 2 pi radians over the wavelength, because the wavelength tells you how long it takes you in distance to get from the start of the wave to the finish of the wave where you're back again, right? So if k equals 2 pi times the wavelength, let's just play around with the numbers real briefly. Right? And we can actually keep that up with the imaginary unit. This is our wave function. Let's imagine that x equals 0. Okay? So if we put 0 in there, then our wave function is going to be the cosine of 0 plus I times the sine of 0. All right, sine of 0 is 0, cosine of 0 is 1, so for this particular wave we were describing, at x equals 0, wave function equals 1, we're at sort of our maximum amplitude. If we instead go to half a wavelength, sorry, you can raise your hand and ask questions at any time. Please interrupt me, don't be afraid. I don't understand a lot of this stuff, so possibly if you ask me a question, I will say, I don't know, and then you'll be relieved, because if I don't know, you don't need to know, right? Yeah?
So the wave, I know that the wave function squared is like the probability of
Uh-huh.
finding an electron. So can you just remind me again with just the wave function?
Okay. Yeah. So, and tell me your name.
Alvaro.
Sorry, say it again.
Alvaro.
Alvaro.
Yeah.
Okay.
Alvaro, yeah.
Cool. Yes. So the wave function squared, as you've learned before, is the probability of finding an electron, and if you integrate it throughout all space, the number is 1, because it has to be. The electron is found somewhere in the universe. Really, really useful piece of information, isn't it? The wave function itself describes the wave properties of the electron. And it has, as we've shown you here, a real and an imaginary component. And that's why we never graph the wave function, because it's impossible to represent the imaginary part of it. So anytime we're representing a wave function, what we're really going to be doing is dealing with the wave function squared. Others? So I don't want us to get lost in the weeds here in the details. But I wanted you to see where this term k comes from, because it's related to wavelength, all right? Such that if we go through, if x equals the wavelength, for example, we can do the same math, and what we would discover is cosine of 2 pi plus I times sine of 2 pi. That puts us right back to where we were at the beginning, where the wave function equals 1. In contrast, if we say, let's let x equal half of a wavelength, let's see what that does to our wave function. If x equals half of a wavelength, let's see, k is 2 pi over the wavelength times half of a wavelength. So what does that turn out to be? All right, what is the cosine of pi? That's 180 degrees, right? So that'd be -1 and 0. Okay, so our wave cycles through. After half a wavelength, it's at negative amplitude, right? And you can play with different distances here. But this constant k tells you something about the wavelength. Now, let's now combine what we know about this constant k from our equation with what we know about wavelength. Remember, the de Broglie postulate was that a wave has momentum, right? So we could actually substitute in this number from the de Broglie relationship for k. So let's let our wave function equal e raised to the I times k is 2 pi over wavelength times x. Let's let that equal e to the I times 2 pi over this wavelength, h over p times x. And then we can start to simplify that. Let's bring p into the numerator. You'd have 2 pi over h times x. And then remembering the definition that h bar equals h over 2 pi, you can condense this down into a really more convenient form where your wave function, just write it down a little clearer, let's see, slightly bigger font, is equal to e raised to the I times p over h bar times x. Okay. Question so far? That's kind of, if you're uncomfortable, it's okay. I'm not going to ask you to reproduce this proof. I just find that when I was reading the text and it would say, oh, this is the momentum operator, or this is the kinetic energy operator, I'd be like, what, do I just take your word for it? I mean, prove it. And so I'm trying to do a little bit of that while not actually doing a very good job of it. So I apologize. Okay. Questions so far? All right. So this is interesting. If we take, well, I think it's interesting. Yeah. So if we take the first derivative, now we're going to do some calculus. If we take the first derivative of the wave function, the fact that the wave function is an exponential is really, really fantastically convenient because the derivative of e to the x is just e to the x, right? And then you use the chain rule if the stuff in the exponential is an actual function of x. So if we take the first derivative of our wave function, that's going to return for us this I times p over h bar times x. But then what comes out of that is I times p over h bar. Because remember, when you take the derivative of something, you first take the derivative of this, and then you got to take the derivative of what's inside in here with respect to x and put it out front. That's I don't know, I can't remember what calculus rule that is, maybe chain rule or something, I don't know. Or another way to rewrite this is just I times p over h bar times the wave function. Okay, now hang on here because we're going to do some things that you maybe didn't know you could do in calculus. All right, first, we're going to divide both sides of that by the wave function. So the wave function goes away. Let me rewrite this here so I'm not drawing over stuff that we already have. I over h times p times the wave function. So we'll divide both sides by that wave function. Now we have some weird d over dx equals I over h bar times p. Alternatively, we can rearrange that to momentum equals h bar over I times d over dx. We have just derived what's called the momentum operator. And what that means is if you apply this function to a wave function, you will get as an answer momentum times the wave function. Let's show that that's the case. And sometimes we'll represent an operator with a little hat. Most of the time I'll forget to do that. But so let's apply this operator. And the operator is just a function that you're going to apply to something else, to the wave function. So that's going to equal h bar over I times the first derivative of the wave function with respect to x. Well, what did we just say the first derivative of the wave function with respect to x was? I over h bar times p times the wave function. So when you apply the momentum operator to the wave function, you get momentum. All right? So people will use this, and you can use it on any wave function if you want to know what the momentum is. And that will give you momentum as a function of the wave, and you can plug in whatever coordinates you want. Alternatively, you might want to know what is the overall momentum of this wave integrated through all space, and there's a way to do that that we'll talk about a little bit later. All right. Questions so far? Samantha, I thought maybe you were...
Yeah, I'm just thinking, I remember learning all this in PChem, but I guess my question is kind of why do we need the operator for momentum? I just don't remember that.
Okay, yeah, so the question is why do we need the operator? And one of the coolest things about wave functions is if you know what the wave function is, you already know everything that can be known about that particle in that particular configuration. And the operators are ways of extracting information from the wave function. So you want to know its momentum? Okay, this is the function you use. You want to know its energy? There's another thing you use. And if you want to know, for example, what the average position of your particle is, you can find that out with the wave function as well. So all of those operators give you pieces of information that are embedded in the wave function. Don't know that that's the best explanation. Okay, one reason we care about the wave function though, or about the momentum, is that what we really would like to know about the wave function is its energy. Because in organic chemistry we care a lot about energies of electrons. That's where all the interesting stuff happens. And so we can actually use our definition for the momentum operator to get some energy term. So I don't know if you remember learning in physics that the kinetic energy of a particle, and sometimes people will call this T instead of kinetic energy. I don't really care about that. Is 1/2 times mass times velocity squared. And maybe you remember that from thinking, okay, well, if I drop a ball from this height and it has this potential energy, how much kinetic energy does it have at the bottom? Well, and remembering that the definition of momentum is mass times velocity, we can actually rearrange this kinetic energy definition to be momentum squared over 2 times mass. And then if we want to derive a kinetic energy operator, all we have to do is plug in our momentum operator from here, and it works. That's the really cool thing about operators, is they're functions that give you information about the wave function, but you can use the operator in physics formulas as though it were that quantity. So now we can use the momentum operator to tell us what the kinetic energy operator should be. So let's go ahead and plug that in. H bar over I times d over dx squared divided by 2m. Okay, well, h bar squared, that's fine, that's a constant. What's I squared? Right, I equals the square root of -1, so I squared has to be -1, so we'll put a negative there. Divide by 2m, and then when you take d over dx squared, this is kind of bizarre, but it actually becomes the second derivative. Okay, so d over dx is the first derivative of the function with respect to x. You square it and you get the second derivative. Okay? And sometimes we'll expand, as soon as we start talking about electrons around nuclei, we're going to need more than one dimension. And so you'll sometimes see people represent this as an upside down delta squared. That means a derivative in all 3 dimensions. And sometimes people will change from x, y, z to spherical polar coordinates because it's more convenient that way, except for me because I don't understand them. But the key idea here is that the kinetic energy of a wave function is related to its second derivative. Okay, great. This is highly useful, thank you, right? But it's more useful than you think. Let's do just a little bit of reminding ourselves what the second derivative actually means. Okay? So, and what we're going to do now is not even with a wave function. Let's just, let's imagine a parabola. Okay? What does the first derivative mean of a function? instantaneous slope, right? That means if I take individual points along this line and then I run a tangent to the line at each of these points, that's the first derivative, right? And if we were to plot those instantaneous slopes, here's some function and here's x. Now let's plot the first derivative of the function with respect to x versus x. What we would see is, let's see, what would we see? Slope would be, I'm sorry. Somebody said a straight line, and you're right. I just had to get myself oriented. This should be 0. Here is x. So in this part of our graph, the slope is negative, right? So we'd be somewhere here. Eventually, it goes through the bottom where the slope equals 0, and then it goes positive again, right? So that's what the first derivative of that function looks like. Okay. Then what is the second derivative? It's just the first derivative of the first derivative, right? So if in that case we would take the slope at each of these points again, but in this case they're all the same. So the second derivative we would see if we were to plot it is just going to be a straight line wherever, you know, that whatever that slope is. Okay. I'm sorry. I realize we're kind of rushing through that, and so I'm making some mistakes. But, you know, let's suppose the slope is 2. Then it's sort of constant throughout all of that. People will describe the second derivative as the slope of the slope, or how fast the slope is changing, or the curvature of the function. Okay? And that's important because it leads us to a really key conclusion in organic chemistry about electron delocalization. Okay? But let me illustrate this point with some things from the particle in a box thing that you probably learned in PChem. Do you remember the particle in a box where you have, it's really kind of dumb, you have some box where at the edge of the box, let's say this is 0 and this is A, at the edge of the box energy goes to infinity at both edges of the box, and you allow the particle to exist. It can't exist outside the box because energy equals infinity. But if you solve the Schrodinger equation for this particle, what you come up with are, what happened here? Sorry, computer went to sleep. I need to turn off the screensaver. When you solve the particle in a box, you get sort of discrete energy levels that the particle can exist at. And the first one is basically a wave that looks like this, and the second one is a wave that looks like this, and the third one is a wave that looks like this, and so on. These are basically standing waves, and if you've never seen one of these, you sort of go get a slinky and play around with it. You can make a standing wave. So this is the energy level of the first, this is the energy level of the second, this is the energy level of the third. One of the things that I teach my sophomore organic students is that when you're thinking about waves, places where the wave goes through 0 are called nodes, and the more nodes a wave has, the higher in energy it is. And that's true, but that comes from this idea that the kinetic energy operator for a wave is equal to or depends on the second derivative of the wave function. It turns out, let's imagine what the second derivative is. I'll tell you that and I just was learning this morning, the equation for the wave functions in particle in a box is something like this. 2 over a, which is the length of the box, times sine of n pi x divided by a, where n is an integer, equals 1, 2, 3, and so on. And I did the math to show that, well, if you do the math, the second derivative of this wave function with respect to x, you get an answer that looks like this: 2 n squared times pi squared over a squared times the wave function. And then if you use what we have here for the kinetic energy operator, you can come to the conclusion that energy equals, well, remind yourself that energy equals minus h bar squared times 2m times the second derivative, which we've said is this. So look at what that second derivative does to the wave function. N equals 1 here, n equals 2, n equals 3. You can do the math, and when n equals 1, this number is smaller, right? The kinetic energy of that wave, and again, this is just the second derivative of the wave function, but the kinetic energy of this wave here is lower than the wave where n equals 2. That seems obvious. It may seem obvious to you, but the idea here is that wave functions that have less curvature are lower in energy. All right? Now, how does that affect organic chemistry? Well, have you ever heard that electron delocalization is stabilizing? Do you remember learning about resonance as an explanation in undergrad OChem and how resonance delocalization lowers the energy of the electrons? Well, now it's not just because your professor told you so, it's because it has to be that way, because the energy of a wave function that's spread out, a wave function that's more spread out is going to have less curvature and therefore less kinetic energy. All right? So, and you know, if you could imagine each of these being an electron, I've tried to demonstrate for you that the second derivative of this function is smaller in magnitude than the second derivative of this function, which is smaller in magnitude than the second derivative of that function. Another consequence of what we've just talked about, okay, so the idea that electron delocalization is stabilizing is a conclusion, a very important conclusion that we get from this description of the kinetic energy operator. And the second thing that we get is that the more nodes a wave function has, the higher in energy it must be. Simply because the only way you go through 0 more times is by having a more curved function, having a higher second derivative. Okay. So that was a kind of a convoluted and long winding path to get to the conclusion that something you learned in sophomore organic was actually true. But again, I want you to remember that the reason delocalization is stabilizing is because of the nature of the wave function and where we get the kinetic energy of the wave function from. All right, what else? Questions? Yeah?
Just to clarify, you said that wave functions that have less curvature, they have less energy?
Uh-huh.
Okay.
Yep. So in this particle in a box, the lowest energy wave function is always going to be the one that has the minimum curvature, no nodes. And actually, you know, if you sort of squint and imagine, this kind of wave function sort of looks like just a spherical s orbital. This one kind of looks like a p orbital with a node in the middle. So this is where these rules stayed the same even when you change the geometry. Yeah?
So is electron delocalization increasing your A, or is it decreasing your nodes?
Oh, that's fascinating. Is electron delocalization increasing the A or increasing the number of... Decreasing the A or decreasing the number of nodes? The answer to that may not be quite as simple. Usually when we're talking about delocalization in chemistry, we're talking about comparing a situation where you don't have resonance, the electrons are all in this place, to a situation where they're spread out over more space. And so that's certainly part of it. I would think that perhaps that's increasing the A. I think that's a reasonable way to interpret it.
Okay.
Yeah. Cool. Other questions? All right. Therefore what? Well, we're going to now talk about, we've just talked about kinetic energy. And in particle in a box, potential energy you sort of ignore because you're basically saying it's zero in the place we care about and infinity everywhere else. But that's cheating. And that's not the way that reality works. So in general, we're going to use an equation to define the wave function. And it's Schrodinger's famous equation. H, which is the Hamiltonian operator, times your wave function. And that's not Alexander Hamilton, that's some other Hamilton, equals energy times the wave function. By the way, this year my son Adam, who's 10, is in the 5th grade, and he has Mrs. Ingalls at Vineyard Elementary School, and she... for much of the year, has her students learn about American history by learning the lyrics to some of the Hamilton songs. Not a lot of the Act 2 stuff, which is a little more adult than they're prepared for. But so they end up practicing this and reenacting it on stage. So Adam really wants to be Alexander Hamilton, and we've been working on the I can't remember whether it's in Guns and Ships or something else. Anyway, we've been working on some of the rapping, and he's getting pretty good at it. I'm not particularly good. With the appropriate words bleeped out. Okay, H is the Hamiltonian. This is an operator that when we apply it to the wave function, returns the wave function and energy, which is a real number and is a constant for that wave function. Okay, what is the Hamiltonian operator? Well, it's actually more simple than you think. What is the energy of a particle? The energy of a particle should be equal to its kinetic energy plus potential energy. So if we want the Hamiltonian operator, we're going to need a kinetic energy operator and a potential energy operator. PE stands for potential energy. Okay? We talked about what the kinetic energy operator is, so we can just plug that in right now. D squared over dx squared. Or if we wanted to expand our definition, let's just use that delta so that we can be in multiple dimensions instead of just x. But that I think delta squared equals the second derivative with respect to x and the second derivative with respect to y and the second derivative with respect to z, and that's multivariable calculus, and you're reaching the end of the line in terms of my understanding of maths. So there we will sort of have to leave it. What about the potential energy operator? Well, in an atom, how do you describe the potential energy of an electron? What's the relationship? What's the law that governs positively charged nucleus and negatively charged electron? Say what? Coulomb. Coulomb's law, right? That says the force between two charges is related to the magnitude of the charges and the distance between them, right? And then you can use Coulomb's law and integrate it with respect to distance, and you get energy. So the potential energy operator for one electron near a nucleus is going to be equal to let's say the charge of the electron, the charge of the nucleus, and then you've got to have some constants there, 4 pi times vacuum permittivity, and then you have 1 over r, where r is the distance between the electron and the nucleus. Okay? We'll just put electron and nucleus there. So if we want the energy, we're going to apply this Hamiltonian to the wave function. Hamiltonian applied to the wave function is going to be the second derivative of the wave function times those constants plus charge of the electron, charge of the nucleus, 4 pi over permittivity, 1 over r, distance between electron and the nucleus, and then multiplied by the wave function. And then that's going to give us the overall energy of the wave function. All right?
So it's h bar squared, right?
Yeah, I always get that wrong. Thank you for pointing that out. I just all over the place. I'm making that mistake. Okay, so you're going to see some equations, but don't. It's easy to panic a little bit when you see all of those numbers, but just sort of reduce it back into your mind to these two things. It's kinetic energy and potential energy. That's all it is. Okay. Now, your text goes on at this point to provide a generalized form of a Hamiltonian for a situation with multiple nuclei and multiple electrons. What I gave you there is 1 electron. Okay? So let's try to talk about that, and we'll probably run out of time. I'll point out that I'm going to need help figuring out what the time is, because somehow in my computer, when I hook the iPad up and start recording the lecture, it's always 9:41 on January the 9th of who knows what year, except we know it was a Tuesday, so we can probably figure out what what possibility of years this is. So it looks like we've got a few minutes left. Let's imagine a molecule, and we're going to have n nuclei, where n is an integer. We're going to have little n electrons, because you can't have half of an electron. Let's let little m with an e equal the mass of the electron. Let's see, let's let big M with the subscript A equal the mass of nucleus A, where nuclei are designated A, B, C, D, and so on. Let's let Z with the subscript A equal the charge on nucleus A. Oh, actually, we're going to be even sneakier than that. Is going to be the number of protons in nucleus A. E is going to just be charge of an electron or a proton. There's a sign issue in there that we'll deal with. Let's see. RAI is going to be the distance between the electron I and nucleus A. RAB is going to be the distance between nucleus A and nucleus B. So we're sort of setting up the hydrogen atom, right? And then, and that, as they say, is that. I guess we're done. It's okay. Don't worry about it. We're good. All right, we'll pause there. We're, several pages into chapter 14, so feel free to review this and go a little bit further. When we talk next time, we're going to take all of that mess, write out a Hamiltonian for a generalized molecule, and then we're going to simplify it and turn it into something that we can actually do stuff with. Okay? All right, see you next time.